Since the electric field is a vector field, we can define other physical quantities that are something like we would use and understand for other vector fields. So I'm going to go back to the velocity field of that fire that I showed you earlier in a different video. The flux we're going to define as the vector field dotted into the area, a small area, and integrated over the area. Okay, so what does this mean? Well, here's a loop. It's just meant to be a single loop. If I rotate it a little bit, it gets thinner. And if I rotate it all the way around that vertical axis, then you see that it's just a very narrow hoop. So I'll bring it back again. In this orientation right here, you certainly see a large area, but since the wind is going to the right, none of the air passes through that hoop. So there is no flux of air through the hoop. In that orientation, rotated about 45 degrees or so, quite a bit more air flows through the hoop. And when I rotate it all the way by 90 degrees so that you just see the edge of the hoop, then the biggest area is exposed to the wind, and so the largest amount of wind, the biggest flux, flows through the hoop at that point. This formula just helps you calculate that. E is the vector field. We'll be using electric field, of course, but the picture here shows a velocity field, so it would just be a V instead of an E. dA is an infinitesimal area, and it has a direction. Now the direction that we choose for, you could figure it out by looking at this dot product, but the direction we choose for the infinitesimal area is perpendicular to the surface of the area. So the surface of the area right now is a vertical plane away from us, away from this picture. And so perpendicular to a vertical plane away from this picture is a direction to the right. So dA points to the right. If I back this up a little bit, rotate it back around, dA right now either points directly toward us or directly away from us. In any case, it's perpendicular to the surface of that hoop. So you can see what's happening. dA, the area, is to the right. The velocity field is to the right, so the dot product is a maximum. And you find the maximum flux here. Here, dA is toward us, the velocity field is to the right, so the dot product is 0, and you find no flux through that hoop, which is a physically sensible thing to find because no air flows through that hoop here, and a lot of air flows through that hoop there. So we use the same kind of definition when we talk about electric fields and electric flux. So let's go back and see how this plays out. Let's go back to the dipole field that we had seen before. We'll talk about Gauss's law in a second. I just want to bring in a surface. Now, this is a three-dimensional field. It's not a two-dimensional field, so I'm going to have trouble drawing three-dimensional pictures. When I draw a circle like this, I mean it to be a sphere, so that it completely encloses that negative charge right there. That's what I mean this picture to show you. This green circle encloses the negative charge. Now, Gauss's law tells us that the electric flux out of a closed surface depends on the charge enclosed. In fact, it's proportional to the charge enclosed. If you put more charge in, there will be more flux out of the surface, and then here's a constant that makes this an equation. This is a sphere, and there's a negative charge inside. So the flux out is going to be negative. In other words, there's flux in. This is pretty obvious from the picture that you see here, that the electric field points inward everywhere. Now we have a reason for giving a direction to dA. We had dA perpendicular to the surface. So right here, dA would be pointing like this, but is it perpendicular out or perpendicular in? And since we're talking about the flux out of a closed surface, dA is a line that is perpendicularly out, is a vector that's perpendicularly out of that closed surface. So negative charge inside, Q enclosed is negative. That means the flux out of this closed surface, this sphere that surrounds the thing, is negative. In other words, there's a flux inward. You can tell that the flux is, first of all, it looks like it's inward because there's arrows pointing in. But you also have, you can tell the sign is correct because dA points out and E, the vector field E, points in. So there's 180 degrees difference between them. Cosine of 180 degrees is -1. When you integrate that over the whole area, you find out that there's a net flux inward. What if we move this surface somewhere else? Well, let's surround the positive charge. Now Q enclosed is positive. So there is a positive flux out, and you can see it works out the same way. Now all the lines point outward. What if we move the circle somewhere else? No charge enclosed. Plus, there's no plus charge. There's no charge at all inside here. But nevertheless, there's a flux through this part of it. There's electric field coming in this bottom part here. But the top part, there's the same electric fields coming out. Exactly the same. I don't necessarily, it looks the same here because it's symmetric, and in fact it is the same. Gauss's law in fact tells us that it must be the same coming out as coming in because the total charge enclosed is 0. So whatever field line comes in also goes back out again. I can make this giant sphere surround both of these charges. Now the total charge enclosed, 0 still. It's got a negative charge, got a positive charge. They cancel each other out. How can the total charge enclosed be 0? That means the flux, if Gauss's law is correct, the flux that points out is 0. Again, down at the bottom, you have flux coming out. These field lines come out. But up the top, you have this similar kind of flux coming in, the field lines coming in. In fact, every field line that goes out of that sphere comes back into the sphere again. And you see that because the total charge enclosed is 0, the total flux to the surface is 0. So I can shrink that back down. I can move it to different places. There's still no charge in here. So every field line that comes in goes back out again. So that's the essence of Gauss's law.